This is the first video of the TLA Plus video course. Each video in the course is meant to be viewed in conjunction with a web page. You should stop the video and click on the page's How to View button for useful tips on viewing the video. If you're viewing this video by itself, search the web for TLA Plus video course to find its associated web page. This video explains what TLA Plus is and why you may want to use it. Subsequent videos explain how to use it. And I thought I told you to click on the How to View button. What is TLA Plus? TLA Plus is a language for the high-level modeling of digital systems. It has tools for checking those high-level models. The most important of those tools is the TLC model checker. Another tool is TLA-PS, the TLA Plus proof system. But writing and checking proofs is a lot of work, and it will rarely be used by engineers. There's also the TLA Plus toolbox, an integrated development environment for writing specifications and running the tools on them. Digital systems include algorithms, programs, and computer systems. For those digital systems, high level means at the design level, above the code level. TLA Plus is used to model critical parts of digital systems, while abstracting away both less critical parts and lower-level implementation details. TLA Plus was designed for modeling concurrent and distributed systems. It can help you find and correct design errors, including errors that are extremely difficult to detect by testing, before you write a single line of code. If you design such systems and care about whether they work properly, you should be using TLA Plus or some other method for precisely specifying and checking your designs. I don't know exactly what else TLA Plus is useful for. In the small amount of programming that I do, sometimes I find it to be very useful. Sometimes it's of no use. I do know that for most computer programmers and engineers, TLA Plus provides a new way of thinking about what they do, and that this way of thinking can make them better programmers and engineers, even in cases where the TLA Plus language and tools are not useful. Abstraction. What kind of clown am I, claiming that I know what can make you think better? Why should you pay attention to me? This is not the time to be modest. I have done seminal research in the theory of concurrent and distributed systems, for which I won the Turing Award. You can stop the video now and look me up on the web. I've been a theoretician. I've invented algorithms and proved theorems. But I understand the needs of computer engineers who build real systems, and my research always had practical goals. My Paxos algorithm is widely used to implement fault-tolerant distributed systems. My most important contributions have not been solutions to recognized problems, but rather precisely stating important problems that had not been recognized because they were obscured by irrelevant details. This ability to recognize fundamental ideas is why my time clocks paper is still required reading in university system building courses 40 years after it was written. The process of simplification by removing irrelevant details is called abstraction. Abstraction is perhaps the most important part of engineering. Only through abstraction can we understand complex systems. And we can't get systems right if we don't understand them. I'm very good at abstraction, and I believe that using TLA Plus will teach you to be better at it. Here's what Brannon Batson, a former Intel engineer, said. When quoting what people wrote, I have made some small changes to eliminate unimportant details while preserving the intended meaning. Brannon said, the hard part of learning to write TLA Plus specs is learning to think abstractly about the system. With experience, engineers learn how to do it. Being able to think abstractly improves their design process.
What engineers say about TLA+. All this talk of abstraction is pretty abstract. If you're an engineer, you're probably not looking for an education in abstraction. You want something that will help you design systems now. So you probably want to know more about what engineers think of TLA+. Engineers in industry who build complex systems usually don't write about how they do it. Fortunately, there was one exception, a team at Amazon Web Services. Amazon is currently the leading provider of cloud services, and Amazon Web Services builds and maintains their cloud infrastructure. They build large, complex systems, and they care about getting them right because their customers rely on them. I have no official connection with Amazon, but Chris Newcomb, who was then at Amazon Web Services, contacted me with some questions about TLA+, and he told me a little about how they were using it. I suggested that they write a paper about their experience, and the result was How Amazon Web Services Uses Formal Methods by Chris and others. Here's a quote from the paper. Amazon engineers have used TLA+ on 10 large, complex real-world systems. In each, TLA+ has added significant value, either finding subtle bugs we are sure we would not have found by other means, or giving us enough understanding and confidence to make aggressive performance optimizations without sacrificing correctness. Amazon now has 7 teams using TLA+, with encouragement from senior management and technical leadership. Engineers from entry-level to principal have been able to learn TLA+ from scratch and get useful results in 2 to 3 weeks. They use TLA+ on 10 systems. That number 10 came from late 2013. By sometime in 2014, they had used it in 14 systems. I don't have any later information. You might want to stop the video now and download the complete paper. Precise high-level models are called specifications. TLA+ can specify algorithms and high-level system designs. But you can't automatically generate code from a TLA+ specification. So what good is a spec if it doesn't produce code? Instead of writing a spec, why not spend the time improving the code? This book describes how a real-time operating system was designed using TLA+. The team that built the system was led by Eric Verhulst. Here is what he wrote to me about their experience using TLA+. The TLA+ abstraction helped a lot in coming to a much cleaner architecture. We witnessed firsthand the brainwashing done by years of C programming. One of the results was that the code size is about 10 times less than the previous version. 10 times less than the previous version. The previous version was flown on the European Space Agency's Rosetta spacecraft that orbited a comet from 2014 to 2016. And when you're building a spacecraft, you try to make the code that goes into it small. You don't get a factor of 10 reduction in the size of code that flies in a spacecraft by better coding. You get it by coming to a cleaner architecture. And an architecture is described by a higher level specification, higher than the code level. They described the architecture as a TLA+ spec and debugged it using the TLA+ tools. Don't expect TLA+ to yield such a reduction in code size on your project. This is just one case. But remember what the Amazon Web Services people wrote. In every case, TLA+ has added significant value. Specifying and testing above the code level is crucial when designing concurrent or distributed systems. What can you check with TLA+?
We use TLA+ to try to ensure that the systems we build work right. Working right means satisfying certain properties. The class of properties that we can check with TLA+ are ones that express conditions on individual executions. One example of such a property is the system doesn't produce a wrong answer. You can examine an individual execution and see whether or not it produced a wrong answer. The system satisfies this property if and only if every possible execution satisfies it. Here's a property that TLA Plus can't check. 99% of system executions produce the right answer. This doesn't express a condition on an individual execution.
The basic abstraction.
The basic abstraction underlying TLA Plus is that an execution of a digital system is represented as a sequence of discrete steps. There are three important ideas here: sequence, discrete, and step. Let's start with discrete. A digital system is a physical system in which we can abstract its continuous evolution as a sequence of discrete events. The first self-powered digital system was the escapement clock. Although all the parts of the clock move continuously, we can describe the real clock by an abstract clock that advances in discrete ticks. A computer is also a continuously evolving physical system, designed so we can abstract the execution of a program by the computer as consisting of discrete steps. What about sequence? It may seem strange to describe a concurrent system in which multiple things can be going on at the same time as a sequence of steps. We know that it's possible to do this because we can simulate a concurrent system with a sequential program. As you learn TLA Plus, you will see that it's not just possible, it's simple and it works really well. What's a step? TLA Plus describes a step as a state change. An execution is represented as a sequence of states, and a step is the change from one state to the next. I find this very natural because in most sciences, systems are modeled by a state that changes with time. Most often, the state is described as changing continuously, but we model digital systems by a state that changes in discrete steps. As in most sciences, TLA Plus describes a state as an assignment of values to variables.
State machines.
An execution of a digital system is represented as a sequence of states. Let's call a sequence of states a behavior, so an execution of a digital system is represented as a behavior, where a behavior is a sequence of states. We want to describe all the possible executions of a system, which means specifying all its possible behaviors. How do we do that? People have used many ways of describing digital systems. Here are a few: programming languages, Turing machines, lots of different kinds of automata, hardware description languages. Their executions can all be described as behaviors. But we can do better. We can abstract them all as what I call state machines. A state machine is described by two things: all its possible initial states and what the possible next states are that can follow any given state. The state machine halts if it reaches a state for which there is no possible next state. A state is an assignment of values to variables. So to describe a state machine, we must describe three things: what the variables are, what the possible initial values of the variables are, and what the relation is between the values of the variables in the current state and their possible values in the next state.
A tiny example.
The example is a simple C program. It's not quite legal C because ANSI C requires main to return an int. But it's obvious what this program should do, except for the function SUMNumber. Let's assume that a call to SUMNumber returns an arbitrarily chosen number from 0 to 1000, and that it can return different numbers in different executions. Let's not worry about how SUMNumber is implemented in C. An obvious way to represent this program as a state machine is with a single variable I. Let's look at one possible execution. Here's the initial state. It's a state that assigns the value 0 to I. It's the only possible initial state because in C, this declaration initializes I to 0. In the second state, I equals 42 because the call of some number happened to return 42. Execution of the third statement increments I, producing the third state in which I equals 43. Okay, how do we describe this tiny program as a state machine?
Remember, we must describe these three things: the variables, their initial values, and the relation between their values in the current state and their possible values in the next state. We're representing this program with the single variable I. There's only one possible initial value of I, namely 0. What about 2, the relation between the current value of I and its possible values in the next state? Let's look at I's possible next value when its current value is 43. In this behavior, there is no possible next value because the program has terminated. Let's look at another possible execution in which the call of some number returned the number 43. In this execution, when the current value of I is 43, its next value must be 44. This execution and this execution require different next values of I for the same current value 43. So it's impossible to represent the program as a state machine in this way.
The problem is that the value of I is only part of the program's state. There's another part of the state that specifies what statement is to be executed next. That part of the state is called the control state. So let's introduce another variable called PC for program control to represent the control state. When PC equals the string start, it means that the first assignment statement is to be executed next. PC equal to the string middle means that the second assignment statement is to be executed next. And PC equals done means that the program has finished and there is nothing left to execute. The initial value of I is 0, and the initial value of PC is the string start. And now we can describe the relation between the current values of I and PC and their possible next values. If the current value of PC equals start, then the next value of I can be any number in the set of integers from 0 through 1,000. And the next value of PC is the string middle. If not, if the current value of PC equals middle, then the next value of I equals the current value of I plus 1. And the next value of PC is the string done. Otherwise, the only remaining possibility is that PC equals done, and the program has finished. So there are no next values of I and PC. Okay, this isn't very easy to read. It's simpler and more elegant in TLA Plus because it's written as a mathematical formula. But we'll get to that later. State machines are much simpler than programs. In a state machine, all parts of the state are represented the same way as the values of variables. In programs, different parts of the state are represented differently. There are the values of the variables, there's the control state, there's the call stack, there's the heap, etc., etc. Those different parts of the state are represented differently in programs because they're implemented differently. State machines eliminate those low-level implementation details. State machines provide a single, simple abstraction. In this course, you will see that TLA Plus is an elegant, extremely expressive language for describing state machines. This lecture introduced state machines as a simple, general method of describing computer systems. The next lecture shows how our example of a tiny C program can be described with mathematics, and how that mathematics is expressed in TLA+. It's the first step on the path of learning to specify real systems in TLA+.